Today we'll take a look at a combination of two circuit elements, a capacitor and an inductor. That's all we have in this circuit. Now this circuit is similar to a mass spring system. This is something you've studied earlier, that if you pull this mass to one side and release it, then this system will oscillate. Similarity seems strange, but you will be surprised to see that the parallel between the two is exact, and we are also going to write the same differential equation for both the cases. Now if you are wondering that why the name LC oscillations for this simple circuit, which is made up of just an inductor and a capacitor. See, once we discuss the working of the circuit, you will see that in this combination the charge, the potential difference and the current in the circuit vary sinusoidally with a time period of t and an angular frequency of omega. Hence the name LC oscillations. Okay, now let's take a look at this, that how does this work. See, initially the capacitor is charged. Let's say this plate carries a positive charge and this carries a negative charge, and this is connected to a inductor. See, the starting point is similar to the case where in the mass spring system the mass would be pulled to one side and released, and then it would oscillate. In the mass spring system there is continuous exchange of energy between the kinetic energy of the mass and the potential energy of the spring, but the total energy of the system always remains constant. Similarly, in this case, there is an exchange of energy between the electric field of the capacitor and the magnetic field that builds up around the inductor. And the energy stored in the capacitor is given by Q square over 2C, where Q is the charge in the capacitor and C is its capacitance. The energy stored in the magnetic field of the inductor is given by half Li square, where L is the self-inductance and I is the current through the inductor. Just follow these diagrams as I draw them. I'll then explain what do they mean. We have a capacitor and an inductor. In the first case, the capacitor is fully charged and there is an electric field between the plates of the capacitor, and there is no magnetic field around the inductor. In this case, the energy stored in the capacitor is maximum, and the energy stored in the inductor is 0, and the sum of the two energies is the same as this. So this is the same, this is the sum of the two energies. So this is the total energy, this is the energy in the electric field of the capacitor, and this is the energy in the magnetic field around the inductor. In the next stage, the capacitor gets fully discharged. There is a magnetic field present around the inductor, and when the magnetic field around the inductor becomes maximum, at that instance the electric field between the plates of the capacitor is 0, because the plates are fully discharged, and in this case the current is maximum. So if you look at the energy in this case, the energy in the electric field has become 0, the energy in the magnetic field is now maximum, and the sum of the two energies is once again the same. So this is the energy in the electric field, this is the energy in the magnetic field, and this is the total energy E. Now next, the capacitor gets charged once again, and you can see that in this case the polarity gets reversed. So now this plate acquires a negative charge and this plate is positively charged, once again the electric field is maximum, so the energy in the electric field is maximum. The energy in case of the inductor is 0 and the total energy is the same. In the next stage we have a situation similar to the second stage. So we'll have the capacitor completely discharged. The magnetic field around the inductor would be maximum. It's just that the direction of the field lines will be reversed now. So in this case, if you draw the electric field, the magnetic field, then the electric field between the plates of the capacitor is 0. The magnetic field around the inductor is maximum, and the total energy is once again the same as it has been in all these different cases. This is the magnetic field. And now coming to the final stage, we'll be actually back to this, in which you have the capacitor once again charged. So you're back to the original starting point, and the energy distribution would be maximum in the electric field, 0 in the magnetic field, and the total energy would be constant. So now we are going to discuss this energy transfer. So if you just label this as 1, 2, 3, 4 and 5. See, in the first case, when the charged capacitor is connected to the inductor, the capacitor starts to discharge through the inductor, and this means that the current starts flowing in the circuit. So if I were to draw a graph, this is the starting point, which is 1, and then the current starts increasing and it reaches a maximum value at 2. So the current becomes maximum in this case, and at this point of time the magnetic field around the inductor is maximum, and the energy is transferred to the magnetic field, and this now appears around the inductor. The electric field has decreased and the magnetic field builds up as energy is transferred from the electric field to the magnetic field. Gradually the capacitor loses all of its charge and thus also loses its electric field and the energy stored in that field. The energy has now been fully transferred to the magnetic field of the inductor, and the magnetic field is then at its maximum magnitude, as you can see over here, and the current in the inductor in this case is maximum. Now although the capacitor is completely discharged, the current persists and doesn't become zero instantaneously, and now the capacitor begins to get charged with a reverse polarity opposite to that it had initially when we started. Now as the current decreases, the magnetic field also decreases, inducing an EMF in the inductor in the same direction as the current, and this slows down the decrease of the current. Eventually, which is this stage which we've shown over here, the current and the magnetic field reach 0, and now the capacitor is charged with the opposite polarity. After this, the same thing repeats. The capacitor starts getting discharged. It's just that in this case the polarity is reversed, so the current will flow in this direction. So the capacitor starts getting discharged and the electric and the magnetic field around the inductor starts building up. So if I were to draw the current becomes 0 in stage 3, which is this situation over here. After that, since a reverse polarity has built up, so this would be stage 4, when the current is maximum in the opposite direction, and you're back to our original stage, which is stage 5. So you can see that the current in the circuit is varying sinusoidally, hence we said that the name is an LC oscillation. We are going to write a differential equation now for the LC oscillator, and it's actually a little easier if you start with the total energy of the system. So the total energy is the sum of the energy in the electric field plus the energy in the magnetic field, which can be written as Q square over 2C plus half Li square. Now in place of I, the current, we can write dq over dt. So let's first differentiate this expression with respect to time. This is du over dt, and you know that's going to be 0 because the total energy is constant. So this gives us 1 over 2c, and this would be 2q times dq over dt plus half L and 2I times di over dt. Now here we can substitute dq over dt as I, and this is 0. So we get, sorry, you have a bracket over here. So this is 1 by 2c, and this 2 will get cancelled out. So you're left with q by c, and this is I, plus this 2 will also get cancelled out, and you're left with Li di over dt. Now dividing both sides by I cancels out, so you're left with 0 equals q by c plus L times di over dt. And if you want to use the same variable, which is q, that would be L times d2q over dt2 equals 0. Now this is our differential equation, and we're going to look for a solution for this differential equation. This equation, which is d2q over dt2 plus 1 by Lc times q equal to 0, has the same form as an equation which you've learnt earlier, which is the equation for a simple harmonic oscillator, and that equation was d2x over dt2 plus omega naught square x is equal to 0. See, if you don't recall this equation, maybe you can just go through it once. You have to start with F equal to minus kx, because that is the restoring force. Then you write this as m into a, which is mass times acceleration. Then you put the acceleration as a double differentiation of the displacement, and then when you substitute omega naught square equal to k by m, you get this equation which we have over here. Now comparing these two equations, we can see that this term and this term are similar. So we have omega naught square, in this case, is 1 over Lc, which gives us omega naught equals 1 over under root Lc, and hence the frequency of the circuit is 1 over 2 pi root Lc. And this is what we wanted to find out. What is the frequency of this LC oscillator, which means the frequency of the LC oscillator, put this as F naught, is going to depend on the value of the inductance and the capacitance, both. And just as for a simple harmonic oscillator, you have X is equal to A cos omega t plus phi. Similarly over here we have Q is equal to Q naught, which is the amplitude, the maximum charge in the circuit, cos omega t plus phi, where omega is this angular frequency and phi is the initial phase of the circuit. If you recall, in the circuit that we had taken, initially the capacitor was fully charged. The charge on the capacitor was maximum, so Q was equal to Q naught at time t equal to 0. So just putting that into this equation over here, you can see Q naught equals Q naught cos omega t, this becomes 0, plus phi, which gives us cos phi equals 1, or phi is 0. We can write the equation is Q is equal to Q naught cos omega t. To test your understanding, try these questions. The answers are discussed a short while later. Now the answer to the first question is, the principle of conservation of energy leads to the differential equation. In an oscillating LC circuit, energy is exchanged between the electric field of the capacitor and magnetic field of the inductor. In the equation Q equal to Q naught cos omega t plus phi, the phase constant phi is determined by the initial conditions at t equal to 0 in the equation, because when t is equal to 0, then this omega t is 0, so you're left with Q equals Q naught cos phi. So then you can find the value of phi. The total energy of an LC circuit is 3 into 10 to the power minus 6 joules. The maximum energy stored in the capacitor in one cycle is also 3 into 10 to the power minus 6 joules, because this total energy keeps oscillating between the energy stored in the capacitor and the inductor. The LC circuit has an oscillation frequency f naught, which is given by 1 by 2 pi root LC.